And we started at a particular state, right? Let's really just sometimes we call this state a zero state, and then we label all the state using the integers 1, 2, 3 all the way down to b, and then we also label this as -1, -2 all the way down to -8. Right. So we start with this state. The question is that what's the probability we are going to sink at a state at the end, state A at the end. Right. That's the question we are asking, right? So if we start with this state, we are going to take a random walk, right? Walking back and forth, right? Eventually, we are going to hit one of these two states. Right? So when I say sink, that's really just describing the fact that whenever we hit the state, we will not be able to get out. Right? So there will be some chance that we hit the state and some chance state like -A. And there's also some chance that we are going to hit the state -B. And now our question is that what's the probability that we are going to hit state A, right? So there's also a different interpretation. Like what's the probability? So if I'm really just taking a random walk on the real line, what's the on the integers, set of integers then what's the probability we hit -A before I hit positive B? So it's called gambler rule-in. It's really just saying that like imagine there are two gamblers, right? So Alice has $8, and then Bob has $B, right? $B, right? So say that, and it's really just they are really just playing some fair games, right? So for instance, toss a coin. If there's a head, then Alice gets half of the gets $1 from Bob, and otherwise Bob gets $1 from Alice, right? So now this Markov chain, the state here can really just codes the amount of money Alice makes so far, right? So if with half of the probability, the state moved to the state 1, that basically corresponds to Alice makes $1 additional, and otherwise that Alice just lost $1, right? So this kind of gambling, like let's just imagine like these two players just keep gambling until one of them go bankrupt. Like one of them spend up all their monies, right? So in case Bob loses $B, then the whole game stops, and then both of them go home. Like similarly, in case Alice loses $8, everyone go home, right? So now the question is that so they keep doing that, like they will just wait until one of them like spend out all his or her money, right? The question is that what's the probability that Alice is going to get all the money, right? So why this is important, right? So imagine that in an application, right? So imagine that you are playing with a casino, right? With a lot of capitals, right? Say it has 100 million. I'm making something up. Now you are really just bringing 5Ks and try to play with the casino, right? So now the question is that like what's like one of you and casino just keep like doing the same thing, just keep gambling like until like either you go bankrupt or casino go bankrupt. It's a fair game, and then the question is that how likely are you what's the likelihood that casino is going to take up all your monies, right? That would be the question we are looking into. Like even that it turns out that even that the game is fair, like the chance that casino is going to take up all your monies if you do the gambling using this kind of behavior, right? I don't go out until I lose all the money, then this probability of losing all the monies is actually very high, right? So this is the implication of this problem, right? So now we just want to analyze this Markov chain, right? So let's define one thing. PIT would be the probability we are at state I at time t, right? So the chain is the state I, right? So basically that's really just translates into this particular example is really just the probability that Alice has made $I at time t. So one thing we need to notice that is that it's a vague like hand waving argument, but if you look at any of the state, right, this state is transient. In the sense that like there's always a constant probability that when we start moving from this state, we hit one of these endpoints, and then we are never going to be able to head back to the same state, right? So in fact, all the states except the two endpoints are transient states, right? And these two endpoints are not transient states, right? Right. So now the question here is that because the state a minus 1 minus a plus 1 all the way down to b plus minus 1 are all transient. Right. Now we are able to say that pi t limit t goes to infinite is actually 0, right? As we wait much longer, the chance that we are going to hit any of the transient state is really just going to converge to 0. Now let's move back to this probability we are interested in, and let's call this p. This as q. So basically, what's the probability that we are asking? What's the probability that you eventually end up at the point A, right? So now, if we write this q in a second way, we can actually write this use p to represent that, right? So limit t goes to infinite, p negative a t is going to be q, right? So this is really just literally saying that what's the chance that I'm going to eventually be stuck at point negative a, right? This is going to be q, right? So now there's also one thing we need to pay attention. If I want to sum up all the states, the probability mass of all the states, right? This is going to be 1, right? So at the end, like even t goes to infinite, I sum up all the probability, it has to be 1, right? So that also implies that, right? So what we are doing here is that if I look at the state negative a, it's going to eventually we are going to start at here is going to be q, like that's our definition, and everything here in the middle are going to be 0, right? And then if we add up all these three components, it's going to be 1. So right, inevitably the probability that we are going to end up is state B is going to be 1 minus q, right? So that also means that we have this one extra condition, like limit of t goes to infinite, pb t is going to be 1 minus q. So now there's one very important argument is that this is a fair game. Right? Fair game means that like in expectation, the Alice is going to be unable to make any money in general, right? So expectation of WT equal to 0, right? So there's a bit of hand waving things going on, but I hope that that's a reasonable argument here, right? So for any t. So actually, let's not call WT, right? So that's what's written there in the textbook, but we usually call this as XT, right? So basically, it's the state, the state where I am, right? Or really just that the amount of money Alice made. So now here's the crucial step. If in the expectation this is 0, then let me just write this up, right? So this is really just the definition of the expectation, right? I p t I equal to 0, right? So for any finite t, if I want to compute the expectation, it's really just using the definition, right? So what's the probability that I'm end up at a particular state and the amount of money I'm making? So now I have this equality. This equality would be the very crucial point for us to really pull out the q and 1 minus q, right? So if I take the limit, t goes to infinite, right? So this is still 0, but now I can sort of see that, right? So, but we are seeing is that pit equal to 0 if I doesn't equal to negative a or b, and pit equal to to q if I equal to a negative a, right? And then PIT equal to 1 minus q if I equal to b, right? If I use this three relationship to substitute that into the summation here, we will get the simplified thing, right? All the things in between are 0, so t goes to infinite, right? Negative a times p negative a t plus b p b t equal to 0, right? And using the fact that what we were just saying here, right? So basically the limit of p negative a at the time limit is going to be q, and for the same thing of p of bt is going to be 1 minus q, right? Let's really just plug in this two relationship, and then we actually get that the whole thing here together with the limit becomes then q, and the whole thing here together with the limit becomes 1 minus q, right? So negative a times q plus b 1 minus q equal to 0, right? So this implies q equal to a divided by a plus b, right? Actually it's b divided by a plus b. So now let's again look at the interpretation here. If this is Alice, this is Bob. Alice has $8, Bob has $B. When Alice hits 8, when we hit 8, I actually say something wrong. We hit point 8, actually Bob wins. Alice lost all his money, and the probability that Alice loses all his money is actually B divided by A plus B, right? So think of the casino example, right? If I casino, right, and my A is substantially larger than B because casino has more money, right? Look at casino and the gambler. Like the example we have just now, let's see whether we can still pull this back, right? So it's 10 million and 5K, right? That means that A is equal to negative A is equal to negative 10 million and B equal to 5K, right? In this case, right, if I plug in this number is 5K divided by the 10 million, 100 million plus 5K, right? So this is a number that's very small, right? Intuitively, that means that if the casino have more capital, then the likelihood that casino loses all the money is going to be smaller. And you are really just even that, like the moral here is that even you are playing the fair games with the casino, just the fact that the casino has more money, you actually put yourself into an uphill battle. It's the chance that casino get bankrupt before you get bankrupt is going to be very small. Okay, so that's an example. So now let's move to the stationary distribution. Right. Let's write down this definition 7.8. Right. So a stationary distribution of a Markov chain is the probability distribution such that pi bar such that pi bar equal to pi bar times p. Right. That stationary, it's really just says that like if I like there's a distribution, I sample the nodes, the states according to a specific distribution, and then I let the Markov chain run. And in case that like every time we let the Markov chain run, it's really just multiplying the transition probability once. And it's called a stationary distribution. It means that like after I fix this distribution, I let it run, then every single time I get back the same distribution. Then it's called a stationary distribution. Right. So let's start with the lemma 7.7, the theorem 7.7, the first important theorem over here, right? Any finite, irreducible, and ergodic MC has the following property. The first one is that the chain has a unique stationary distribution. And the second one is that for any j and I, the limit of t goes to infinite, pji t exists and is not a function of j. And the third one is that there's an explicit form to write down the stationary distribution. Limit of t goes to infinite, pjt t, which is going to be the same as h 1 over hii. 1 over hii really just means that the expected time to return to I from I. Right. So let me make a number of remarks here, like, although I'm trying to write these things down, really just copying the theorem from 7.7, right? So the theorem has to hold only if when it's finite, irreducible, basically the graph is fully connected and ergodic, right? So it has to also be aperiodic and strongly recurrent, right? A positive recurrent, right? So if any of this, if we are facing a so-called normal Markov chain, then there are quite a number of nice properties. The first property is that the stationary distribution is unique. The second one is that if I really look at this quantity, what's the probability that I end up at state j when I start with state I? What's the probability I end up with state I when I start with state j? When t goes to infinite, it's actually a constant, converged a constant that's not a function of your starting point, and eventually there's an explicit form of this stationary distribution, right? So the explicit form is really expressed as like connect this stationary distribution as the expected time to return to I. Right, so now let's proceed to prove this theorem. We actually don't directly prove the entire things. We rely on a building block we actually don't prove. And this building block is actually quite complicated. So basically it's the entire theorem is powered by a very powerful building block which we don't prove. But again, like, even we don't prove the powerful building block, the reason we still want to connect this building block with the rest of the theorem is really to show you some of the kind of techniques we use in analyzing the Markov chain together. Is really just to give a feeling of the structure of the Markov chain as we walk through inside this proof. Right? So what would be the building block we are using? Right? So we're using a building block. We don't prove. So this is the lemma 7.8, and for any irreducible ergodic Markov chain and any state I, the limit t goes to infinite, pii t exists, and the limit of t goes to infinite, pii t is 1 over hii. Right. So this is so even we don't prove this lemma, we sort of want to give you the intuition of what's going on here. Right. So now let's start with looking at this quantity over here. Imagine like there's a like we are performing a random walk like on a certain Markov chain, and let's really just draw this random walk, like unfold this random walk like so that it behaves like a time series, right? So we start with time equal to 1, that t, now we start with and then our state is I, and then t equal to 2, then let's call this as v2, v3, right? So and then v4, right, and so on and so forth, right? And eventually what we are interested in is that now if I look at a particular time like t equal to t, and you will be like it's the probability so which state we are at, this Markov chain is at this particular time, is going to be a random variable. So we are interested in this probability Vt equal to I. So as t is large enough, right? So you can imagine that we wait for very, very long, and all of a sudden we open this Markov chain. We are not observing this Markov chain for a while, and all of a sudden we open this Markov chain and see what's going on here, right? So now, basically the intuition. Let me start with the intuition, right? So if t, like intuitively, like if t is large enough. Right, so let me just even make it like less rigorous. I say that, let's say that there's a wall, and if I walk long enough, and then anything after this wall will be sufficiently close to infinite, right? So basically, like you can sort of imagine, like another way to imagine that is this one is already an infinite wall, and then if I walk infinite amount of time, I add constant, like infinite plus constant, like up to here it's still called infinite, right? So everything here intuitively is called infinite, right? So now, and second thing we are observing is that if I just take this walk, and the HII, what is the HII? Is the expected time to return to I, right? So HII means that I take a certain walk, and I hit back to I again. Let's say V5 is I. And then I hit I again, right? So every time I hit an I, the distance here, on average, the distance on average is HII, right? So this is what's happening, right? So once a while, I hit an I, right? Right. So and then the distance between two I's are really just expressed by HII here. So now, if I look at entire chain here, right? So if I really zoom in, right? So this is, I start with here, I wait for very long, like this is basically infinite, and then I need to also continue to wait, right? So now, basically, if I just look at the portion of i's that appears, right? So basically, even every HII steps that appears at one I, right? So that you can sort of see the density here is approximately 1 over HII, right? So that really just means that if I walk long enough, 1 over HII portion of the chain is going to be at state I, right? So but on the other hand, if we interpret in a different way, right? So if I look at this probability here, right? So intuitively, if the probability here is going to be P, that also means that the P portion here, P. So let me just claim here, right? So now I want to let me make this claim clear, right? So I want to compute this probability, right? So probability of Vt equal to I, right? Let's call this as P, right? So the interpretation is that for every single point, like P, with P probability that it's an I, right? So if I try this long enough, right? So we also get that P portion of them is going to be I, right? So that's because like you can really think of, imagine that every single point like P fraction of them is I, right? So it's a bit intuitive, and then it's not rigorous, right? But you can sort of see that these are two connected, right? So in case like these two interpretations are the same, then P needs to really be equal to HII, and that's the intuition that's going on here for this lemma, right? So it's not easy to directly prove the entire thing, but if you look at the intuition here, it's really just talking about after T is sufficiently large, the portion of the nodes that are in the random walk that are at a state I, right? Counting things in two different ways, intuitively, right? Now, with this lemma, we are going to prove this theorem 7.7. So this is theorem 7.7, and then we want to be able to prove that, right? So let's start with really just walking through the proof of lemma, the theorem 7.7, right? So we want to first prove that the limit of t goes to infinite pjit equal to limit of t goes to infinite piit equal to hii, 1 over HII, right? So that basically it's the first, one of the statements says that like, so long as you walk long enough, you can actually forget the where you start with. Right? So let's see how can we prove that. Okay, so recall that JIT is really just the probability that I start at the time at J and hit I for the first time at time t. So now, because we are assuming the entire chain is irreducible, we do have this really unsurprising behavior. If I sum up everything, right, it's going to be 1. So that basically means that for that if this is really a convergence statement, and if we want to like unfold this convergence statement into epsilon delta language, it's really just that for any epsilon greater than 0 xx t1, that's a function of epsilon, such that if I sum up everything, t1 ji t greater than equal to 1 minus epsilon. So this is really just the consequence of the definition. Right? So now the next thing we have is that for any j doesn't equal to I, we have pj it equal to sum of k equal to 1 over t j it p I it minus k. Right? Why this is true, right? So this is really just the law of total probability. Right, so we start at a state j, and then after t step, right? So I'm going to after t step, I'm going to hit the node I, and I want to so this is the event we are interested in. So this is the entire event we are interested in. We focus on, and we want to partition the event into a number of disjoint sub-events, what I call. Right? So basically, the sub-event is really just that we condition on what's the first time. The first time I hit I, right? So the first time can really just partition the entire full event, all possible passes, into a number of the collection of all possible passes like into a number of disjoint set, right? So the case 1 is that this first time, like the first time is t equal to 1. Case 2 is the first time is t equal to 2, and so on and so forth, right? So these are really just that you can imagine that I pull out the set of all possible events that are describing from moving to j to I using t steps, right? These are the all possible events, and then I'm really doing the partitioning, right? So this one part of the partitions is really just belongs to the events that has this property, right? The first time to hit the I, the final node I'm at, is at t equal to 1. And the second partition would really just correspond to the second case, and so on and so forth, right? So this is, right, you need to know that it's a partition. When we partition, it's really just that when we want to sum up at the end the whole probability here, I just need to sum up the probability for each of the cases. Right? So the probability for case K is really just that the first time I hit a j at time k, and let me draw this one again. Like, so this is the time interval. This is I. This is j, and this is I, and this is time, right? So here for the case k is really just that at time k I hit, this is time k, I hit the state I, and from time k to time t I move from state I to state I again, right? So this is the I t minus k. So this is for case k. And then if I sum up all possible cases, that's the reason that we come up with this quantity here. Right. So now let's also try to do a bit of this the rescaling over here, right? So this is the crucial. Right, so let's do a bit of the inequality, right? So if I really just sum up with k equal to 1 over 1 to t1, and r j I k and p I t minus k less than equal to what, right? So that then we sort of want to say that have a statement that for any t greater than equal to t1, we do have this inequality. What's the inequality we are having? K equal to 1 to t k j I p I t minus k, right? So you really just see that we have more terms here, right? Compared to this one with this one, right? There are more terms here. Right? There's more terms here. That's the reason we have an inequality. Right? So now, and here that this is really just the as we have, right? So we are seeing this one, right? So we apply this star like this equality here, that we get a p j I t. So, sorry, so this is PJIT, yes. Right. So now we also use it, now let's proceed, right? So we also use the fact that the limit t goes to infinite, PIIT exists. And the t1 is actually a finite number, right? This finite number is really defined here, right? So, where's the definition, right? So this is the definition of t1 over here, right? So once we have this definition of t1, then we can do a bit of the manipulation. I'm really just copying out the table and explaining each of the steps in detail. Probability if that goes to infinite, tj is greater than equal to limit of t goes to infinite, sum of k equal to 1 to t1 j I k and p t minus k and I, right? So so let me just be a bit careful here, right? The summation here is t1, right? So basically this is repeating, the equation here is repeating what we are seeing here, right? So I'm taking the limit here, then this part I'm copying here, and the left hand side is really the right hand side on this inequality is really just the left hand side here. We have the t1 showing up here, right? So now this actually can help us we sort of have this the first term is independent of the t, right? So we can push this limit inside. That gives us this one, k equal to 1 over t1 j I k, and limit of t goes to infinite, p I t minus k. Right. This is actually I. Sorry, there's a typo over here. Sorry, this is actually not I. There was no typo. Right. So now we are really seeing this term we really like here. Right. So t goes to infinite, t minus k is actually the same as limit of t goes to infinite, p I k. Right. So we are sort of having this one. Right. So this is the limit of t goes to infinite, p I t times sum up of everything. Right. So now this part is actually it's actually the part of this result we want, and here is really using the definition of that this is greater than equal to 1 minus epsilon. Right. So this is greater than equal to t goes to infinite, p I t and 1 minus epsilon. Right. Right. So you can sort of see that like magically when we do the operations over here, we can sort of push out the term over here, the term that's in terms of I to I, right? So when I push out these terms here, then it's somehow like if with some sort of manipulations, right? So we sort of need to fix the t1 so that the k is going to be in general like much smaller than t as the t goes to infinite. After we do that, like eventually we are actually able to decouple this I term from the term that's a function of j. And then we can also say that, well, this term is sufficiently close to 1 over epsilon. Right? And we can also do the same thing, like the other direction, will be similar, right? Right. So now eventually we are actually getting something like that, like p p j I t limit of t goes to infinite is going to greater than equal to 1 minus epsilon times limit the p I t t goes to infinite and greater than equal to 1 plus epsilon limit of t goes to infinite p I t. Right. So when I let epsilon equal to 0, then basically that implies pjit limit t goes to infinite is the same as limit of t goes to infinite piit. Right. So that's the reason that we managed to prove one part of the result. Let's see which part of the result we are proving here. Right. So this is really just the second part of results, and so this is really just saying that this is the same as limit of t goes to infinite piit. Everyone is the piit. Right. So the somehow the j component is really just going to disappear using the positive recurrent using the recurrent property of the j's node. Right. So now we need to be able to prove that the second thing is the stationary distribution, the second part, right? So the pi I equal to HII, or 1 over HII is a stationary distribution. Right. How do we prove that? Right. So we really just want to use the definition. The definition is really just the pi equal to pi times p, right? So this is what we need to prove. Right. So let's first verify that we really need to do two things, right? The first thing is to verify that pi is indeed a distribution. Right. So what we are seeing here is that this one, as we described just now, is the same as a limit of t goes to infinite piit. So this is what we have from the lemma what's the number here, 7.8, right? So now we do have the limit of t goes to infinite piit t, and let's see how can we prove that. How can we prove that? Like using this property, we want to prove that if I sum up everything equal to 1 to n, this is going to 1. We need to prove that. Right. So how do we do that? Let's see what the textbook is doing. Limit t goes to infinite equal to 0 to n pjin. Right. If I look at this one, so this is basically pjit. Right. This is basically talking about eventually where. So let's even first put aside the limit. Right. This whole part here is talking about with t steps. If I start with j, what's eventually where I'm going to end up with? I'm going to end up with only I has to end up with one of the nodes in the Markov chains, right? So if I sum up everything, this is going to be 1, right? So this is again just the law of total probability, right? So now this is also, let me really just do that, like substitute, let's exchange this two term, right? I equal to 0 to n limit t goes to infinite pjit, right? So and then this one is really using our results just now is the same as I equal to n over 1 over n limit t goes to infinite piit, right? And then this is again like using the fact that the equality we are drawing here is really just that I equal to 0 to n pi I, right? So this is really just showing that this is a stationary distribution. Sometimes I draw that start with 1 and sometimes we start with 0. Like just be careful, like I make some typos from time to time, right? Right. So now this is the first part of the proving that this is a stationary distribution, right? The next thing is that we observe that this one, right? So the next we have this one, observations. Pj I t plus 1 equal to sum of k equal to 0 to n pj I t pki. Right, so this is really just the idea of the dynamic programming, right? So if, right, so within t plus 1 step, I'm moving from j to I, and how can I do the decomposition, right? So I can look at the last step where, so it's in the t step, like where do I end up with? Like I can end up with one of the states from 0 to n, right? So then I do the decomposition, right? So from step 1 to step t, then it can be j to k, and then from step t to t plus 1 is k to I, right? So if I can also use a picture to illustrate this idea, right? So there are a total number of t plus 1 steps, right? So I look at this t plus the t step, right? So this is t plus 1 step. All right. So all possible, there are a lot of possibilities, right? All the possibilities I list up here. Right. So if eventually I'm going to start from j and end up with I, so these are the state 0, state 1, state 2, all the way down to n, right? So if I need to end up with I can ask the question, what's the state that's right before me? It has to be one of them, right? So if the state that's right before I hit I is going to be 0, then what's happening is that I move from j to I to k to 0. Within the first t step, and then move that from k from state 0 or state k to I in the last step, right? So this is how I'm summing up here for the first term k equal to 0. And then I sum up everything here, and then after I sum up everything here, then I got this summation here, and that's the reason that this summation is true, right? So pj I t plus 1 equal to sum of k equal to 0 and pj k n plus tki, right? So now I take the limit at the both sides, right? So also let the limit of both sides, right? So when I take the limit, right? So this is basically t plus 1 I, like this is what we are seeing here, right? So let's also see what's the limit we are seeing on the right hand side. Limit of t goes to infinite, pj k and then pki, right? So this is actually the same again, like we can sort of use the result we have been using, that the pjkt is going to be insensitive to the starting point. It would be also be the same as the limit of t goes to infinite, pkkt, right? This is actually the pi k, right? So what we are seeing here is that this is actually the pi I. Pi I equal to pi k summation of nk equal to 0 to m pi k pki, right? So this is eventually what we are getting here, right? So if you express that into the matrix form, it's pi equal to pi p. So that's the reason that we verify that this is indeed a stationary distribution, right? So now it's also pretty straightforward to see that, like, this is unique, right? Let's see how do I prove the uniqueness, right? Suppose there were another stationary distribution, let's say phi, such that the phi equal to phi p, right? So using the same argument, we actually also have phi I equal to k equal to 0 to m phi k pk I t, right? So now what we are doing here is that we can again like just let there's a pk I t here, right? So we can sort of like take the limit again, t goes to infinite for to both sides, and then we sort of see phi I equal to k equal to 0 and phi k, limit of the pk I t goes to infinite, right? So this is again, right? This is again the same as pi I, right? So at the end of the day, 5i equal to pi I, k equal to 0 to m phi k, right? Because 5 is a stationary distribution, this is 1, right? So this is pi I. This is how things get done. So here, I think you need to pay attention and be careful to see that eventually where did we use the ergodic property. And so we have to rely on ergodic property. For instance, if we have a bipartite graph, right? So it's a bipartite graph, then actually the distribution is not stationary. So now there's a question that where do we use the stationary distribution, this ergodic property. So this is actually like it's actually a good habit to ask this question that like where did we use, like obviously there are some cases in which like this theorem doesn't hold, and so some cases of the Markov chain this uniqueness property doesn't hold, and in this case the chain is not ergodic, but it seems that our proof didn't use the ergodic property at all, like if you look back like what we have been doing here. Right, so none of the places it actually ever remotely touches the periodic assumption. Right? So it turns out that the very subtle thing or the very obvious thing is really just that when we use this building block, right? So we talk about this building block here, right? So the building block is actually using the ergodic. Right? Without the ergodic, this is not going to hold. Why is that? But this is like not only that this building block is using the ergodic. If you look at this quantity, like even without looking at the 7.8, right? If you look at this quantity p of I to I within t stat, take the limit, right? So in case, like just imagine what happens if the graph is bipartite, right? That really means that the PII t is 0 for t not even, and PII t would be a different number for t is even. Right? Not even is actually odd. So sorry that. So t odd. Right? So we do have these two things together. Right? That really means that if I draw this like this PII like with respect to t, it really looks like that. Sometimes it's non-zero, sometimes it's 0, sometimes it's non-zero, sometimes it's 0, and so on and so forth. Right? So in this case, this limit does not exist anyway. Right. So let me just repeat. If the graph is periodic, then it's not ergodic. If it's not ergodic and periodic, then that really just says that this in this case that this limit doesn't even exist. It's obviously lemma 7.8 doesn't hold. When lemma 7.8 doesn't hold, then all our argument falls apart, right? So at the end of the day, you sort of see that what we have been doing never uses the assumption that the graph is a periodic or ergodic, but this assumption is really needed to prove the uniqueness of this stationary distribution. Okay. So I think that's pretty much for today. Like we are sort of running out of time. We are going to continue our discussion on Markov chains in the next section. Thank you again.